Okay, everybody. Today is our first look into derivatives and beyond looking at these different forms. So these are some of our forms that we've been dealing with already. I have these down as being put on your note card, but I think we actually already put them on our foldable. The one that might be slightly different is this first one, because this first one's really like a combination of the second and the third ones. So taking the derivative at a versus the derivative at x, it's a combination of x's and h's. But this becomes so tedious to do all of this. Any of these forms we've been looking at over the past couple days, it takes a lot of algebraic manipulation to do this. So what I want to do is to start to look for patterns and start thinking about some things in terms of derivatives and finding equations that represent all the slopes of the tangent lines to a function at a point. So we're going to be here. This is 3.3, and this is differentiation rules. So title your notebook that. Once again, pause as I'm going through some things here, back up. If you got questions, shoot me an email. Come to Zoom, and we can discuss some of these things. So let's start thinking about ways that we can not have to do as much work for some of these problems. So for instance, if we know that the derivative of a function is its slope of the tangent line, then if I have a function that is a constant function, let's say f of x is equal to like 1, well, the derivative of that constant function would be all of the slopes of the tangent lines to that function. Well, how do we draw slopes of tangent lines, how do we draw tangent lines to this flat function? And we did this back in the smooth curve left. It's going to be all these flat lines right on top. Those are the tangent lines, even though they touch at every single point. Well, what do all those have in common in terms of their slope? They are all slopes of zeros. So the derivative, pick a different color here, the derivative would just be 0, y equals 0. So if you're taking the derivative of a constant function, let's say y equals 3, its derivative is going to be 0. I don't have to go through all of those limit definitions to figure that out. It works. It's going to come out to be 0, but I don't have to do that because I know the derivative of a constant is always 0. So on your, not your formula card, on your foldable, if I can spell it, foldable, what I want on the outside of the foldable is d dx of a constant, and then inside the foldable is that it's 0. So the derivative of any constants, the derivative of, and I could say, what's the derivative of pi? Well, the function pi would just be a flat line at 3.14. It's going to be 0. So the derivatives of constants is 0. And in terms of physics, if we wanted to think about it with physics, what's our constant function that we deal with physics a lot? Well, it's our acceleration time function. And if we take the derivative of acceleration time, which are constants, it's going to give me a 0 function, which in that case, what is the derivative of acceleration? Well, a change in acceleration is called a jerk. We might not have talked about this in class. Well, since our acceleration is constant, there is no change in acceleration for what we're doing in physics now. That's why we're getting no jerks or 0 jerks, no change in my acceleration. So that relationship would be there too. All right, so let's look up here. All right, there's a lot of work on this page, so don't write anything down. Let's just take a look at some patterns. So the first thing I'm doing is I want to find the derivative of x squared. And so I'm going through and I'm setting everything up. I'm using the x plus h form. And I'm expanding some stuff out and crossing out some terms and evaluating, and eventually the x squareds would cancel out, and the factor out an h, and h is going to cancel out, and then the only thing I'm left with is 2x plus h. H will go to 0, so I get 2x. So the derivative of x squared is 2x. Is that surprising? No, because just think about our position time graphs. They're all parabolas. And what are all our velocity time graphs? Well, they're all linear functions. So the fact that it's a linear function is not a surprise. We've talked about this with a couple classes, I know. Well, the next one, let's do x to the third. So I would have to take x plus h cubed minus x cubed all over h. Here's me expanding it all out, minus f of x all over h, and canceling some stuff out, and eventually I'm going to wind up getting 3x squared. Well, that's interesting. Now the derivative of a cubic winds up becoming a quadratic. Now, if I do it one more time, x to the fourth, any guess of what its derivative is going to be? Well, you can see it right there. It's 4x cubed. So we know that it seems like it's losing a degree, like squareds become linears, cubics become quadratics, quartics become cubics. But what about the terms themselves? X squared becomes 2x. X cubed becomes 3x squared. X to the fourth becomes 4x cubed. Well, it's like that coefficient, that exponent is now the coefficient out in front. Look at my pattern of 2x, 3x squared, 4x cubed, 5x to the fourth, 6x to the fifth. Next one, 7x to the sixth. You got it. 8x to the seventh. So what's going on here? Well, if I look at that pattern, I can see if I have a function of x to some power, its derivative is the power is coming down and the power decreases by 1. And that's going to happen for all polynomial functions, or functions to a power, I should say. So x to the fourth now becomes 4, bring down the power, x cubed. And notice I'm using my good notation here, f prime of x. Y is equal x to the eighth. Well, its derivative, y prime, will be 8, power came down, x to the seventh, power reduces by 1. So this is at what we call the power rule. So this is the power rule of derivatives. So we want to put this onto our foldable. Again, on the outside is the derivative of x to the nth, and on the inside is nx to the n minus 1. And maybe on the inside, label it power rule. Remember, you can always pause me if I continue on here. Well, what happens when I have a constant that's already in front of the equation? Like if you look at my example, 7x to the fifth. Well, what we can do, and we'll learn tomorrow, is why I can just ignore that 7, leave the constant alone, and just take the derivative of x to the fifth, which we now know is 5x to the fourth, and then multiply the coefficients together, 35x to the fourth. So we can leave constants alone and simply take the derivative, in this case using the power rule, bring the power down and subtract the power by 1. This is called the constant multiple rule, which basically says if I take the derivative of a constant times some function u, well, just leave the constant alone and take the derivative of u, which would be du dx or u prime. So this one's a pretty common one that we're going to use a lot. So once again, we want this on the outside of our foldable and this on the inside of our foldable. Quick example before we go here to the next slide. 5y equals 8x to the fourth. What will its derivative be? Well, it's going to be 8 times the derivative of x to the fourth, which is 4x cubed. So in the end, 32x cubed. So really, eventually, we're going to maybe skip this middle step, and you can just bring this power down and multiply it by the coefficient out in front, since apparently we aren't going to do anything with that coefficient. We'll learn why tomorrow when we discuss something called the product rule. So I've got my constant multiple rule. And then other rules that we're going to use a lot are pretty straightforward. If I'm taking the derivative of 2 terms added together, I simply take the derivative of each term individually. If I take the derivative of 2 terms being subtracted, I'm going to take the derivative of each term individually and subtract. I don't think these are worthy of putting on our foldable because we're going to use them so much they're going to become second nature. So in this case, what's y prime? Well, the derivative of x to the fourth, 4x cubed using the power rule, plus the derivative of 12x. Derivative of 12x. Well, that's x to the first power. Well, that would be 1 times 12, or 12x to the 0. And what's anything to the 0 power? Well, that's just going to be 1, so it's plus 12. But if you think about it, guys, what's this? This is just a linear function, 12x, slope of 12. What are all the slopes to the tangent lines to the function 12x? Well, they're all going to have slopes of 12. So that's why that came out to be 12. So we can use the power rule, or I can just think of linear functions. The derivative of any linear function is just going to be the slope, because all the slopes are going to be the same as the function itself. Next one. So I got a trinomial here. Just take the derivative of each term individually. Derivative of x to the fourth, use the power rule, 4x cubed, minus derivative of 2x squared, that's 4x, and the derivative of a constant, well, that's a flat line, that slopes are all going to be 0. Do you have to write the 0? No, but I'm showing it anyway. So how about a question like this? This is where we're now leading to. I would like to know what are all the horizontal tangents to this function. So if a function has a horizontal tangent, I'm just drawing some random old function, this would be a horizontal tangent right at the top here, and this would be a horizontal tangent right here. And what do horizontal tangents have in common? Well, their slopes are 0. So I want to figure out when are the slopes of this function equal to 0. Well, do I have something that represents all of the slopes of the function? Yeah, the derivative. So what's the derivative? This is the one we just did a minute ago. I'm not going to put the plus 0 this time. So I now want to I don't want to figure out what is the slope at a particular point. I want to figure out what is the particular point that has a slope of 0. I'm working backwards. Okay, so now I have to solve this equation. Well, a little simple factoring. So I'll factor out a 4x out of both terms. I think I can keep factoring. So now if I set each individual term equal to 0 by the zero product property, multiplying terms together, one of the terms has to be equal to 0. So 4x equals 0 gives me 0. X plus 1 equals 0, well, that gives me negative 1. And x minus 1 equals 0, x equals 1. Now, did I answer the question? I don't think so. I actually want to know what are the horizontal tangents, or what are the horizontal tangent lines. Well, horizontal lines are y equals equations, not x equals. These x values are telling me where the slope is going to have a slope of 0. Now I want to know what is the actual equation. Well, I don't know the equations of the tangent lines. That's what I'm trying to get. But I do know that they're tangent to my original function. So I can just use the original function's values to tell me what the y value is, which would ultimately tell me what the equation of the tangent line is. So when x equals 0, what does y equal in the original equation? Well, that one's easy. That's y equals 2. When x equals negative 1 in the original equation, what does y equal? I'll do this over to the side. So negative 1 to the fourth minus 2 times negative 1 squared plus 1. So it looks like I get y equals 1. And if I do x equals 1, that's going to be 1 minus 2 plus 2. Looks like it's also y equals 1. So I got two distinct ones. Y equals 2 and y equals 1 are my horizontal tangents, but it's happening at 3 different values. Well, why is that? Well, let's look at the original function is this quartic function, which is the blue function, and it has 3 places where the tangent line is going to have a 0 slope or be horizontal. So that's why 2 of them are exactly the same, because they have the same minimum value right there at 1. So there are really 3 places where the slope is 0 or the tangent line is horizontal, but it's happening at 2 different points there. So that's a good graphical representation of what we just calculated and what we just found, and see where my values are. Slope of 0 at negative 1, slope of 0 at 1, and a slope of 0 at 0, all 3 values. Something else to also consider is the fact that the derivative, 4x cubed minus 4, that's what we set equal to 0 and solve. Well, when I set this equal to 0, that would be where this graph, my red graph, I'm graphing the cubic, would equal 0. So if I set the first derivative equal to 0, that means its graph of the first derivative is the places where it would be 0, so it's x-intercepts. So the x-intercepts of the derivative represent the zero slopes of the original function. So finding some relationships there. So those are types of things that we want to look at with our graphs, and the graphing activity we did recently should have been pointing out some of those places where the original function has a slope of 0, the derivative is going to have an x-intercept, touching it and or crossing it at that point. Or I should say touching or crossing. So we'll keep looking at more relationships of graphs and their derivatives as we continue. Another thing to just keep in mind to reinforce what we saw before, these negative slopes over here mean that the derivative is negative below. These positive slopes over here means that the derivative right here is positive or above the x-axis. All right, how about this question? Common question on the AP exam. So f of x is 3x minus x, piecewise function for x is less than 1, and ax squared plus bx for x value is greater than or equal to 1. So the couple questions here. If the function is continuous for all values of x, what's the relationship between a and b? So if the function's continuous, remember if the function's continuous, then the function value and the limit value have to be equal as x approaches, in this case, 1, my point of discontinuity. So I'm going to say that the limit as x approaches 1 of the left side, so this would be the left-hand limit, has to be equal to the limit as x approaches 1 from the right-hand side, which would be dictated by, just a, where is that? Ax squared plus bx. And now I know the function's going to be defined at 1 because of the equal to sign in that 1 inequality up there. All right, so let's evaluate this limit. Limit as x approaches 1 of the left side. This would be my left-hand limit as x approaches 1. So that's going to be 3 minus 1, so that's going to be 2. And over here, if limit as x approaches 1 of ax squared plus bx, I'm just substituting a 1 in. So it looks like I get a times 1 squared plus b times 1, which is just a plus b. So there's my relationship. The relationship that has to be between a and b is that a and b have to add up to 2. Well, now I want to find a and b values so that the function is both continuous and differentiable. So continuous and differentiable. So continuity, we're already, at this point, we're going to guarantee it for all values. It's happening to the left and right of 1 because these are just continuous functions themselves. But at 1, I'm forcing the limits to be equal to each other at 1, the left and the right-hand limits. So therefore, I'm going to then need to check on differentiability, which means that the derivatives coming in from the left has to equal the derivatives coming in from the right. So therefore, the limit as x approaches 1 of the derivative of the left, well, what's the derivative coming in from the left? What's the derivative of 3 minus x? Well, the derivative of 3 is 0. The derivative of minus x, well, that's going to be negative 1. If I do the power rule to it, it's going to be negative 1x to the 0, which is negative 1. Or think of it as a linear function. Negative x has slopes of negative 1 all the time. And the limit as x approaches 1 coming in from the right of the derivative. Okay, what's the derivative of x squared? Well, that's 2x to the first. So that's going to be a times 2 times x. Plus now the derivative of bx, well, that's a linear function, so it's just going to be its slope. You can do it with the power rule in it, but that's just going to be b. So and as x approaches 1, well, the constant function over here on the left is going to be negative 1, just always staying negative 1. And limit as x approaches 1 of the derivatives coming in from the right, well, that's going to be 2a plus b, just letting x be equal to 1. So now, how do I solve for a and b? Well, I think I've got a system of equations that I can set up. There's my relationship between them being continuous. I'm at this point going to subtract the two equations or multiply through by negative 1. It looks like I get negative 3 equals a. And if I take that and substitute it into either of the two equations, it looks like I get b is equal to negative 5 if I solve. Nope, b is equal to 5, positive 5. So there we go. That's my a and b value that will guarantee both continuity and differentiability. So this function will be both continuous and differentiable everywhere, including at 1. Nice and smooth going through there. All right, so at this point, need to do a little practice. We had a lot of stuff here. We learned some derivative rules, and we learned some applications of using those derivative rules. So go into Canvas and see some practice problems for today.